Welcome back to The Explainer. Today, we're uncorking the chemistry behind two compounds you probably use all the time without even thinking about it: alcohols and ethers. So let's get right into it.
Yeah, I know, it sounds like the setup for a really weird joke, right? But the punchline is chemistry. All three of these are built from two very closely related families of organic compounds. And trust me, by the time we're done here, you're going to see exactly how they're all connected.
So first up, we've got alcohols. And the thing you always look for, the dead giveaway, is this little attachment right here, the hydroxyl group, or -OH. You can think of this as the molecule's business end. It's the part that defines pretty much everything an alcohol does.
And then we have their chemical cousins, the ethers. See that difference? That oxygen atom, it's not hanging off the end anymore. Nope, it's wedged right in the middle. Kind of like a suspension bridge holding two carbon-based groups together.
Okay, so this is the absolute key point. An alcohol's hydroxyl group is like a reactive handle that's just itching to grab onto other molecules. But the ether's oxygen? That's more like a super stable, unreactive bridge. And that one teeny tiny structural difference, well, it changes absolutely everything about how they behave. All right, here's our game plan for today. First, we'll see just how they related, then we're going to crack the code on how they're named. After that, we'll dive into how they can have the same exact parts but be totally different molecules. Then we'll see why alcohols and water get along so well, and finally, we'll check out some of the cool chemical transformations they can go through.
Let's kick things off with what makes them so similar and yet so different. Turns out, it all boils down to their shared recipe. Now this is really fascinating. Both alcohols and ethers can be built from the exact same general formula. So for any given number of carbons, they have the same shopping list of atoms. This right here is our first big clue as to how they're related.
Okay, moving on, let's see how this difference in structure gets baked right into their names. You know, chemists need a way to be incredibly specific, and for that, they've got this kind of universal language.
And that language is called the IUPAC system. Now don't let the name scare you. It's not some stuffy old rule book. It's more like a blueprint. If you know the code, you can look at any chemical name and know exactly how that molecule is put together atom by atom.
Naming an alcohol follows 4 simple steps, but there is one golden rule you have to remember. The OH group is the star of the show. It gets all the attention. You find the longest carbon chain it's attached to, and you number that chain so the OH gets the lowest possible number. Everything else is just built around that.
Ethers are named a little differently. What we do is we find the longer carbon chain and call that the parent. The shorter chain, along with that oxygen bridge, is treated like a single attachment, which we call an alkoxy group. It's why you get names like methoxyethane.
Okay, get ready for a really cool, kind of mind-bending idea that connects everything we've talked about so far. It's all about how you can have the exact same atoms and build completely different molecules. And that is the whole concept of isomers. Think of it like this. You have a specific pile of Lego bricks. You could use them to build a car, right? Or you could take those exact same bricks, take them apart, and build a house. Same parts, totally different structure. And in chemistry, believe me, structure is everything.
So, let's go back to our formula, C4H10O. One way you could build it is with a nice straight chain of 4 carbons. Simple enough. But you could also snap those same carbons together in a branched T shape. See? Same parts, but the carbon skeleton itself is different. That's a chain isomer.
All right, now what if we keep the carbon skeleton the same, but we just move the OH group? You could attach it to a carbon at the end of the chain, or you could move it to one in the middle. That's a positional isomer. The core structure is the same, but the active part has a new address. And here it is, the magic trick that connects our whole story: functional isomers. With that same C4H10O parts list, you can do a complete molecular remodel. Rearrange the atoms, and bam! Your alcohol, with its reactive OH handle, transforms into a stable ether. Same formula, but a completely different type of molecule. And that is why they're chemical cousins.
So we know they're built differently, but what does that actually mean in the real world? How does that change their behavior? Let's find out, starting with how they get along, or, don't, with water.
Well, that OH group on an alcohol basically acts like a powerful little magnet for water molecules. It can form these really special connections called hydrogen bonds, and that's what lets the alcohol dissolve so easily in water. Ethers, on the other hand, just can't do this nearly as well, which makes them much less soluble.
But of course, there's a catch.
For small alcohols, that little OH magnet is plenty strong enough to pull the whole molecule into water, no problem. But as that greasy, water-hating carbon chain gets longer and longer, like you see with heptanol, it starts to overwhelm the pull of that one little OH group. The molecule starts acting more like an oil and really struggles to dissolve.
All right, last section. Let's see how that reactive OH handle makes alcohols a total playground for chemists, allowing them to be transformed into all sorts of other useful molecules.
This is where things get really elegant. Take an alcohol, add some acid, and crank the heat to 180 degrees. You'll strip out a water molecule to create a totally new compound, an alkene. But, and here's the cool part, drop that temperature by just 40 degrees and something completely different happens. Two alcohol molecules join hands, lose a water molecule, and form an ether. The outcome is literally controlled by the thermostat.
Oxidation offers another whole set of transformations. Depending on where that OH group is located and the strength of the oxidizing agent you use, you can convert an alcohol into several other useful compounds, like aldehydes or ketones. Once again, the alcohol's initial structure determines its ultimate fate.
So, let's bring it all together. The key takeaway is this. A tiny architectural change, just shifting one oxygen atom, creates two entirely different molecular families. That one simple difference cascades into different names, different properties like solubility, and totally different chemical personalities. It's why one is in your wine and its cousin can be used to start an engine. It's a great question to ponder, really, because once you start to see this hidden language of functional groups and isomers, you realize that this fundamental code of chemistry is written into everything all around us.